So this is especially relevant and timely as we chat about research one-pagers in the new year, or as some folks work towards objectives that aren't going to see a whole lot of progress in the year scale, like ethics in AI. So we hope to shed some light onto what long-term research looks like, and we're really excited to have Mike join us.
I guess I would like to start with a short bio of Mike, and then we will go on the few small instructions and then the conversation. Mike started his career, or he joined the field in an exciting time and did his bachelor's in the Brown University and took a gap year. And then in 1982, he started his PhD at University of California at San Diego with David Rumelhart. 5 years later, he started his postdoc in Toronto with Professor Hinton, and after that he joined the faculty at University of Colorado at Boulder, in which he served for 30 years doing research mostly in the intersection of computer science and cognitive science. And in 2018, recently, Mike joined the Google Brain team, and he does have a decent amount of responsibilities from NeurIPS, Secretary of NeurIPS, and former chair of Cognitive Science Society. And overall, he's interested in human-centric artificial intelligence, which involves designing machine learning methods that leverage insights from human cognition and building machine learning-based software tools to help people better learn, remember, and make decisions and feedback. So with that, I'd like to welcome Mike again, and thanks for joining, and everyone, likewise.
Thanks for having me.
I feel like you had a really cool little story about how you got started doing research. Can you tell us a little bit about kind of stumbling into that at Brown?
Yeah, so undergrads at Brown got something like $200 a semester of time on a mainframe computer. And I was taking a neural network class. There were actually neural network classes taught in the 1970s. There's a fellow named Jim Anderson at Brown who studied very simple linear models and recurrent nets. And I was in his class, and so for my project, I decided I was going to use my $200 of university-provided computing time, and I managed to use it up in an afternoon, as you guys can all appreciate. And I had lots of friends who weren't computer science majors, and so I went around and got their $200 credits and managed to burn through about 10 grand of computing and handed in my project to Professor Anderson. And he went wild because he hadn't seen computing on that scale before. And so we ended up writing a book chapter together that ended up in this book called Parallel Models of Associative Memory that Jim Anderson and Jeff Hinton co-edited. And so that was my entree into the field. So.
I wonder what kind of a model it was. Was it a neural network? Maybe I already missed like how big it was.
I'm trying to remember exactly what it did. It was a recurrent net that did pattern completion. So you'd give it part of a visual image and it would fill in the rest. And it was trained with a biologically plausible learning rule. That was, of course, pre-backprop days.
Got it. And like after your bachelor's degree in Brown in the East Coast, you moved to the West Coast to University of Colorado. I guess there's also like a gap year, and we were talking about this. Like, can you tell us maybe a little bit more about like the decision to go to California and do your PhD there?
Yeah, at the time there weren't any groups doing neural networks other than psychologists. And we had this very amazing group with Dave Rumelhart and Jay McClelland that was interested in using neural networks to explain human behavior and model human behavior. And the year I showed up in San Diego, Jeff Hinton had arrived as a postdoc or I think he'd been there a year already. And Michael Jordan was a grad student also in the same program. It's a psychology PhD program at the time. It kind of melded into a cognitive science program a few years later. But it was this amazing confluence of people. I was very, very lucky to be there at the time. And it's when Backprop was developed, and there was just so much going on, and there was so much excitement.
So I'm curious, what did you think research was when you first started your PhD? Did you do any undergrad research? Has your view of kind of what that looks like shifted over time?
Well, I had that project that blossomed into that book chapter, so I had a feeling for what it was about, and I really enjoyed it, and it was really exciting to, everyone on this call appreciates how cool it is when you get a neural network to do something that you weren't anticipating it could do, and it surprises you. So that's what turned me on. And when I started grad school, I also did human experimental work and found points of intersection where the neural network models would have behaviors, and you would want to see if people exhibited the same behaviors, as well as can we use neural networks to explain weird aspects of human behavior. The particular research I started when I was in grad school was studying visual perception, and in particular how people deal with crowded. I was studying word perception. So if you show people two words at the same time and just give them a brief view of the words, they mix up letters of the two words. So even though the two words are physically far apart on the screen, if I show you line and lace, you might see lice and lane, where letters migrate from one word to the other. Far apart in the visual field. It's not like they're sitting on top of each other, so there's just some local spatial uncertainty, as in a convnet. And so my interest was in trying to understand that phenomenon and understand how the brain represents information. And it led to a study of types and tokens. How do we represent letter types and letter tokens? And that topic has just come back up again in my research career. So it's kind of fun to see things go full circle.
Yeah. When was the next time that it resurfaced for you? How many years later was that? Or was it a continual thread through the whole thing?
Well, it's a project just from the last year where we're trying to build models that process multiple objects in the visual field. This is work with Anirudh Goyal at Mila and Yashua and other folks at Mila. And the idea is if you have a display full of bouncing balls, the balls all, let's say, have the same dynamics. And so you need multiple instantiations of the same object concept. And what's the right way to represent that, where we can keep these objects distinct, where we don't have to learn separate knowledge for each object. And so it's really a question of noting that these two balls are two objects of the same type. There's a ball that has this location, a ball that has this location, but they share something in common, this more abstract. And personally, I'm happy if the model makes the same kind of errors people do, but AI folks are trying for something better.
Yeah. So you can go for it, Aku.
I mean, I was planning to going back to the PhD times, like it's like to introduce some nostalgia. It's like sounds like quite interesting times, and maybe like at the time in computer science, from my understanding, there's no neural networks, so it's all psychology. And the main reason researchers are interested in is to understand the human brain better. And I guess like even in psychology, it wasn't a popular field. Like, can you maybe tell us a little bit more about like how did the neural networks and artificial intelligence was being seen, or like neural networks particularly seen around that time? Yeah.
There was definitely a coevolution of AI and cognitive science. And if you look at the two fields, there's a really nice parallel with how they evolved. So prior to the 1980s, both fields were very much symbolic, where the representation of knowledge involved sort of strings of symbols and structures involving symbols and relationships among symbols. And cognitive science adopted the same ideas. I think cognitive science was a bit quicker to pick up on neural networks as a metaphor for how the mind works than AI was. I think at UCSD, we all had this vision that neural networks would be relevant for AI. And I even had a little project that I sent off to AAAI, and I think I mentioned to you that it got rejected, and the reviewers said, we don't really see what these neural networks do with artificial intelligence. And I would kill to find that review somewhere. I know I had it physically on paper, but yeah, that's long since gone. So about 4 years later, there was a grad student in computer science who did basically the same idea that I explored for his PhD thesis, and it got a lot of attention. That's life.
Maybe this is also like a good point to like talk a little bit about the near misses. You mentioned in our previous talk that like you had a lot of near misses. So let's maybe talk first, then like maybe the achievements will be a nice way to close it up. Like, what was your greatest misses? Did you had any? If so,
my whole life is a string of misses. So that was probably the first one. I'd forgotten about counting that one in the mix. It was an information retrieval system using statistical retrieval. After that, I did my thesis. It was a ConvNet, and I actually had developed it pre-backprop and did end up training it with backprop, but the first version I had this sort of random convolutional connectivity that worked pretty well. And I finished my PhD thesis and wrote up the work more from a psychological perspective and decided there really isn't much more to do with ConvNets. That field is kind of over and done with. And I went off to do my postdoc with Jeff, and Jan was there as a postdoc still grinding away on ConvNets. And I said to him, you shouldn't waste your time doing that. Do something different now.
Oh my God, you said that?
Yeah. It's lucky that there are people like Jeff and Jan and Joshua who get ideas and won't let them drop out. I have trouble keeping ideas in my head for more than a week at a time. So I think the secret to success, and I should be the negative example, is to stick with things that you're committed to. I see that Nick is on this call, and he's working on a project with a group of us that he's pushing an idea, and we keep giving him flack and giving him flack, and he just sticks with it, and I admire that so much. We beat him down every day, and he comes back the next day with his new approach. So that was, the ConvNets were the big miss. For my thesis, after my thesis, I also had a little recurrent net with a self-linear connection that could learn gaps in time over long periods of time. And a few years later, when I was in Boulder, I had both Jürgen and Sepp Hochreiter as postdocs at slightly different times. And they added all these stupid gates to my model. And I thought it was really ugly and convoluted and didn't make sense. And they asked me if I wanted to be on the paper, and I said, no, that's a really terrible thing.
I didn't know that. So you could have been in the LSTM or like the famous LSTM paper, but you said no.
I don't quite have the chronology right, because they were working on LSTM before I got to Boulder, but I definitely had the model that had that self-recurrent connection as the sort of way of passing gradients back in time. And obviously it wasn't it wasn't that element that made the idea work, and it wasn't necessarily the gates that made it work, but rather it was holding up to a very large scale that kind of pushed things over the edge. It wasn't, in the 90s, LSTM wasn't a big success. It really took massive computing power to make LSTM work out. Let's see, the next one was I bought an old house and I decided I was going to renovate it, and I was spending all my time renovating my house and not getting any research done. So I started telling people I was building the world's first adaptive neural network house. And at some point, everyone I talked to thought it was a really cool idea. And so at some point we decided we were actually going to do it. And so the house was stripped down to the framing, and I was able to run something like 5 miles of conductor around the house to put sensors all over the place. We had like 75 sensors, and the house could control all the lights and the heating system and water heater and local heater, and built adaptive control systems. And it was very cool. I think we just passed on a link. You would get out of your chair in the study, and the lights would go on in the bedroom because it would predict you're walking into the bedroom next. And if you woke up in the middle of the night and walked into the bathroom, it would turn the lights on but dim them. And so it was all this sort of predictive optimal control system. And it had these dual objectives of both making me happy and trying to minimize energy consumption. And those goals don't necessarily work together. So it would keep playing this reinforcement learning game with me, where it would sort of push the temperature down and wait for me to complain. And if I didn't complain, the set point would become lower and lower. And it all worked, and I kept it running for about 10 years. And at that time, there was a lightning storm and kind of fried the thing. And it was definitely my 15 minutes of where that's the thing that people sort of knew about what I had done. But again, I got contacted by a few home automation companies, and no home automation companies were really getting much leverage with their ideas, even though it sold really well to say, here's a house that programs itself. You don't have to program it to do things, because that was the main limitation with home automation. But it wasn't until the internet took off that people saw the value of being able to remotely control stuff. So those darn Nest people, I hope there's no Nest people here. They came along and then claimed that they were the first to do what they were doing. But I have a NeurIPS paper from the early 90s called the neurothermostat that is doing exactly, what the Nest claims to be doing.
It's not too late. You could still make a splash in that scene.
John Platt did hook me up with the Nest people, and they were willing to talk to me for an hour, and I think they got annoyed with me. They didn't invite me back to any more meetings, but they were definitely getting to the point where they were doing what we had been seriously doing in the early 90s, like so fancier control models, fancier predictive models, and really trying to characterize individual behavior patterns.
Yeah. So sad about the lightning strike. That's an unfortunate way for it to go.
It was very sad. I actually saw sparks flying. I had all this low voltage electronics around the house that was built by undergraduates who had never held a soldering iron before.
Oh my goodness.
Kind of amazing that it lasted 10 years, but I literally saw sparks flying out of those sockets in the wall. So I'm just glad the house didn't burn down.
Yeah, did you get out when that happened?
No, it wasn't that threatening.
Okay, all right.
Some sort of surge.
It's a lot of faith that you have in the undergrad.
I just wanted to add, like, that kind of like running the system at 10, and I encourage everyone. I put the link into the chat. 10 years of automation. I think there was miles of conductor. That seems like a super interesting and successful project. And it's definitely an interesting paper that's from 1990s, I guess, from very early times. I would like to paste another link, so that I will do it with your permission. The photo from the Connectionist Summer School, 86. So
yeah, it's a great picture.
So this was, I guess, during your PhD, and this a lot of probably familiar faces in the same picture. I don't know. I wanted to ask, how was it, the feeling around those times in 1960, 86 summer, what people were talking about?
Yeah, so first of all, let me tell folks what the summer school was. So the neural net people called themselves connectionists. I know there's this sort of revisionist history where people say, oh, connectionism was pre-neural networks, pre-deep learning, but it was just another name, right? Like everything got rebranded deep learning, but there was no difference whatsoever between people who called themselves connectionists and people who say they do deep learning. It was just sort of the phrase that came along with the field at the time.
So I'm gonna swirl back around and say that the learning that we should take from the near misses is don't listen to your advisors, and timing is important, right? That's right, right?
Yeah. What's missing from this story is we all know the successes, the Jans and Jeffs and Yashuas, but we don't know all the people who had ideas and stuck with them, and those ideas went nowhere at all.
Yes. Yeah. I think it's I think you have actually, you can maybe give yourself a little more credit. You have actually worked on a lot of the same problems for quite a long time. Maybe they've taken slightly different forms or transformed, but a lot of the inspiration seems like pretty similar. You have a pretty long thread going from the beginning of your PhD all the way through now with this story that you just told about a project you started last year. Do you want to talk about at what point during your research journey you started to tease out what those threads were? Now you have a pretty coherent vision of four different ideas that you're personally interested in, but when did those start to materialize?
Yeah, I feel like there's some researchers who are very strategic, who say, this is the area I want to have impact in. And this word impact is a word that I've started to use since coming to Google, since we're all evaluated on impact. And it's actually a really good word to keep in mind. And I wish, looking back, that I had kept that in mind. My focus wasn't sort of, this is the area I want, but I'd wake up in the morning and I'd look what was in my inbox and see what looked interesting and start working on that. And it was very bottom-up directed, whoever I would be chatting with or whatever paper I would happen to read. And I wish it had been more top-down directed toward having a goal, having impact. But when you look back, just because your brain follows sort of logical threads, there is some natural structure to the things you work on. And in my case, I don't realize it until after the fact. And after the fact, you realize, oh, I've just had the same idea over and over and over again, sort of cast in slightly different terms. But at least in my case, it's not a strategic sort of direction. It's more, the state of my brain today is going to be similar to the state of my brain tomorrow. So the ideas sort of evolve very naturally. But I do encourage folks to be strategic more than I have been.
I guess like I will be the one who just like keeps back in time and want to talk about like the old days, but I'll do it one more time. So like after your postdoc, we didn't really talk too much about like kind of research that you've been doing in those days, and then there's like this very long time period where you were in University of Colorado, and there's like a lot of interesting and diverse and impactful research that you I use the impact too. I guess I've been in Google for long enough. Research that you've been doing. Can you maybe tell a little bit more about that, like human cognition modeling and human optimization? Like what led you to start working in those areas? And yeah.
So the neural network field split toward folks who were seriously believing that neural networks would be useful for AI. And that was the direction that Jan and Yashua and other folks like Hugo who came along went in. And between the rest of us who said, we see these as pretty good proxies for thinking about how the brain computes and we can better understand human thought, And in particular, I'm interested in more the psychological level, the sort of behavioral level, to explain, for example, how memory works. That is, when you learn some new information, it's a fact, memory decays over time, and what's the nature of that memory decay, and what sort of mechanisms can we build that explains that decay. And so my initial interest was in building models that could explain behavioral data. So psychologists would go off and run experiments, and you'd have these graphs showing sort of memory as a function of time, or perceptual confusions as a function of display composition. And then you build a model and run the model and try to get it to replicate the exact pattern of human behavior. And you could call that accomplishment. You have these two graphs side by side, one's the human data, one's the model, and feel like the model was some sort of explanation of the human data. And that's an endeavor that a lot of folks in cognitive engage in. It wasn't terribly satisfying after some point, because just like we all know, we can tweak our neural networks to kind of get them to work for one data set and get some results we like. You don't really believe that you have a robust algorithm. You don't really believe you've found a sort of deep principle of cognition in my case. And it didn't feel satisfying just being able to explain data, predict new data that you could run experiments to verify. And I thought it would be much more cool if you could use the models to actually help people learn and remember and perceive. So my focus kind of switched to saying, if we really believe these models, then we should be able to use them in a predictive way where I can use the model as a proxy. Why is Jeff Hinton's face in here?
I think he just joined our call.
Well, that makes me very nervous. I've been talking about you the last 20 minutes, Jeff.
I intended to go to this, but I forgot, and I just realized I forgot.
Welcome.
We could start all over again.
No need. I think I know most of it.
Okay, where were we? Now I'm extra nervous. I'm going to block out Jeff's little frame so that I don't know he's
using the modeling to help humans learn better. I guess that was the direction.
Right. So if you really believe these cognitive models, if you really believe it's a model of the mechanisms going on in the mind, then that model should be useful for predicting human behavior, and you could use it as a proxy for people and do optimization with a model. You could ask, for example, if you're trying to teach people some information, what's the best way to teach people? Well, you can run lots and lots of human experiments, but it's much more efficient to run experiments on a model. It's less costly, much faster. So the game is to optimization with models and then see if, in fact, the conditions that the model predicts will be optimal are actually useful for helping people to learn and perceive.
So now that Jeff's here, Mike, you want to talk about some of your greatest successes?
Jeff, I told them about all the things I blew, like thinking ConvNets were over and done with in 1987. And
I thought that too.
I'll tell you a Jeff story. So when I was in Toronto, my only publication with Jeff is with Jeff and Rich Zemmel, who was starting grad school then. And it was an idea that I can't remember what we called it, but let me call it
Traffic.
0.0. And it had the same flavor of capsules, that you were trying to learn structural relations between features and activate detectors. And when capsules came along, I was like, oh, even Jeff has the same idea, and he cycles back around and around over the years, and each time it becomes a little more sophisticated. So the fact that I do it too, it made me feel a little better to see Jeff doing it as well.
I can tell you a useful trick. Am I? No, I'm live. I can tell you a useful trick, which is, as you get older, you think you should get more up to date, but actually, as you get older, you should go back to older and older ideas. I'm back to 1973 now, and I had a really good idea in 1973.
I told folks about the Parallel Models of Associative Memory book. So maybe we should mine that book to see.
I got mail about that today from some publisher who wants to republish it because they've noticed people want it and it's out of print.
Cool.
I'll try to get a link to that book and try to share it after the talk. I'm super curious too. I wanted to go back, circle back to the human learning part, and I think Catherine asked about the successes. I know we talked about this project where you partnered with a school and then made an experiment about learning and memory. Could you maybe tell us about that? And
yeah, sure. So this was a project that I thought had no chance of working, and I had this really amazing student, Rob Lindsay, and he decided he was going to devote his life to this project, but it would be very exciting if it did work, and it did turn out to work. So the idea was we developed these memory models that could predict how you forget information over time as a function of your past experience with a particular item. The items here were foreign language vocabulary words. So you study some vocabulary, you forget it over time, you study it again, you remember it a little bit longer, and it turns out that memory decays slightly more slowly the more you study stuff, and it depends on the exact temporal distribution of practice. So we had models that could predict how memory decayed as a function of that temporal distribution of practice. And the idea was to try scheduling material for review that would lead to the greatest robustness in memory, the greatest persistence in memory. So what happened was we had this amazing middle school teacher who taught about 300 Spanish language students, which seemed like a huge number for Google. And he gave us half an hour a week that kids could use our software to review material they'd already covered in the course. So every week there was some new material they had to master, and then whatever time was left, which boiled down to about half an hour a week, they would review the material that we chose for them to review. And we did this beautifully controlled experiment where for each student, a third of the items they had to learn were split into each of 3 experimental conditions. And in one condition, the material was studied the way the students like to study it, which means that they just saw the new material which they were about to be quizzed on. They all wanted to study the new material because they had a quiz at the end of the week. The second arm of this experiment studied a sort of spaced practice schedule that said, let's do what psychologists would generically recommend, which is you should review material after about a week or 2 after you've initially been exposed to it, if you want to remember it for a duration of a few months. And then the third arm was this personalized strategy that used an individual's entire study history to predict which item they would benefit most from studying at a particular moment, so that when it was called on to serve a review trial, it would choose the item that the student should benefit most from. And so mind you, this was sort of 30 minutes a week out of maybe 5 hours the kids are putting into this class, and they're doing stuff in the classroom, they're doing homework, and this was just 30 minutes that they would sit off to the side and use some Chromebooks that we gave to the school. And at the end of the semester, they took in a quiz on sort of cumulative course material for the whole semester, and we got a 16.5% improvement in retention a month after the end of course of the course material with this personalized strategy over these other 2 review strategies. And so it was very successful. The teacher liked it so much, he kept us involved, and we joined with several other teachers, and the project scaled up, and we ran it for 2 or 3 years, and it really replicated well. We got very nice, robust results. The only issue was that the students didn't like reviewing. They thought that reviewing was a waste of their time because, first of all, they had a quiz each week and they wanted to study the material for the quiz, not stuff that they didn't need that week for the quiz. But also because reviewing is hard and studying new material is easier because it's fresh in your mind. But it turns out that to best bolster memory, you want to study the material right as you're about to forget it. So that sort of painful review is really, it's a no pain, no gain kind of phenomenon for memory. And the kids actually broke the software. At some point, they figured out that if they closed the window where they were reviewing material and they reopened it, it would go back to letting them study the new material for 10 minutes before it would go to review. So we lost a semester or 2 of data before we found out that they'd come up with this strategy. We were seeing very few review trials and we didn't know why. And the teacher let us correct that the next semester by saying, let's align the students' goals with the software's goals. And we'll just tell the students, your grade is based on how you perform using the software. So whatever the software serves you, that's the material you should know. And then it worked very well again. So that was a fun in-class experiment. I'm now involved in a project here called Tivoli that's doing foreign language training for ESL learners practicing English. These are people who already know English pretty well. I think they're focusing on South American audience. And the hope is to be able to use some of these same strategies within Google. Although at the moment, the experiment that we're running today, I see little chat messages popping up in the left corner. The experiment they're running today is whether we can use a chat bot to serve as a instructor for the student, as an agent to work with the students, as opposed to a pre-scripted dialogue or a human instructor.
Can I ask a question? Yeah. Just to show that I used to be a professor. Did you run a control where you took the reviewing that was tailored to a particular student, and you gave that reviewing tailored to one student to a different student, just to check there wasn't something special about the tailored stuff?
We didn't do that specific control in this study. We have done interchanges in other memory studies, because what really matters is not only what material the student's seen in the past, but success or failure. If all that mattered was what sequence you've shown someone, if you've shown someone 2 students the same sequences, then if the sequence was all that mattered, then you would predict they could use the same schedule. But what's really important is using the feedback from the student. So we didn't do that in this experiment. We did controls that were randomized in that we kept the overall distribution of the material the same. So there was a certain proportion from this week, the previous week, the week before, in the personalized schedule, and we used that same distribution, but randomly chose items rather than the items. So they were matched for sort of the age of the material in terms of the student's experience, but we didn't interchange the kind of recommendations. I'm working on a project now where we do that interchange, but it's more with a sort of incentive scheme where we're trying to keep people focused on long-term goals, which is another project I can talk about. Do folks know that Jeff has a psychology PhD?
Not a PhD.
No?
No. My PhD is in intelligentsia artificiosa.
Was that something you made up?
No, my undergraduate degree was
Psychology.
in psychology,
Ah, okay.
but I only did a year of it because at Cambridge you can do different things every year.
And you're being very nice because I'm on the call. I think normally you would add, and it was worth about a year.
I wouldn't go that far.
Wanted to ask, like, in terms of like memory retention, maybe there's also something to learn in research, like repeating the all things instead of just going for the deadline. I don't know. I just wanted to ask you a question. Do you think like the memory retention research, can you apply? It's a very silly question, I know, but is there anything to apply to doing research?
At the moment, I'm looking at my screen, which is full of windows, and I actually have a strategy of having separate desktops for each project and keeping my notes in certain spots on the desktop. And I find that sort of spatial localization is a really useful memory cue. Memory and spatial representation are intertwined, and it's a lot easier for me to switch projects if I actually switch desktops and go back. And when goddamn Chrome forces me to restart and all the windows end up on the same page, I lose half a day's worth of work because I have to get all the windows back in the same place.
If you work on a project today and it doesn't work today, how many years should you wait before coming back around to the same project?
Oh, that's a good question. I feel like I'd have an idea the next day, so I would not wait very long.
Sometimes I can say something about that. Sometimes you need to wait 17 years. That's what happened with Boltzmann machines. 17 years later, I finally figured out how to make them work better.
And how long for Helmholtz machines?
We don't know yet.
There's probably like some power law distribution of waiting times, and Helmholtz machines are way off on the tail.
Actually, variational autoencoders using the reparameterization trick are Helmholtz machines made to work by Max Welling and Dirk Kimmer. And that was about 17 years.
All right, so that's the answer, Catherine. 17 years.
17 years. All right, I'm on it. See you guys in a couple decades.
Ross, do you want to ask, like?
So there seems to be this kind of, glorification, I think, my impression of ideas versus engineering. At least there was, especially before the whole deep learning revolution. So I guess my question is, in your experience, in your career, was there a big distinction between ideas versus engineering? Do you more generally look at our field as more of a scientific discipline or an engineering discipline?
Well, I come from a different field. Like, as a psychologist, it's much more of an idea and concept field than engineering, and you engineer only to the point of showing a proof of principle. And I think it's a little bit sad how far the field has gone in the other direction, where you can't write a compelling paper unless you've done, you have 5 pages of numbers comparing your model to every other model that's out there. And there should be more value to cool ideas that don't yet scale up that you want to pass on. One of the coolest papers I saw this year in NeurIPS, well, I think Hugo is a co-author on this, was this idea of filtering the outputs of each layer in a developmental manner. I've forgotten what you guys call this, where it's just a very simple idea that you sort of let the network sort of pass this very coarse information initially, and over time it gets refined. And I walked away from NeurIPS with that idea because it was this sort of core little idea. And if you looked at their simulation results, they got away with murder because they weren't getting state of the art as their baseline. So they had nice reviewers, but I'm glad that paper made it through because it was a cool idea. And talk to your co-author Hugo, and there's a developmental literature on sort of the development of the visual system that starts off with a lot of early low pass filtering that gets higher resolution over time. And you guys push that through sort of every level of the model, and it seems to have had a really positive effect. So I like ideas.
I completely agree with that. It's impossible to publish new ideas now, except on archive. I think people should do more, particularly old people, should do more publication on archive and screw the 1% better than something else.
If you ask me my role model to write papers that convey beautiful ideas, it would definitely be Jeff. So.
Your role model, who do you wish you could be when you grow up? Did you have any role models?
Well, Jeff is a pretty damn good one, but I guess I should find a different example since he's right in the room and I've already gushed about him a bit. Dave Rumelhart was a really amazing person. So Dave is the first author on the backprop paper. Jeff is second author, and Ron Williams is the third author. And Dave was a psychologist who was really interested in mechanisms and understanding the brain. And he would just sort of sit there and tinker around all day, and he'd wander up and down the halls, and whoever he ran into in the halls, he'd tell about whatever he was thinking about. And publishing didn't really matter to him. He was just really enjoying having the ideas and playing with the ideas. He developed a bunch of things like softmax and sort of probabilistic formulations of neural network outputs and different loss functions that are based on probabilistic formulations. But it was all done just sort of, he wanted to tinker around, and he did the tinkering himself, and it was just really inspirational. Sorry.
I remember an interaction with Dave where I was talking to him about an idea, and he said, I'm going to have to stop now because I've got to give a lecture in 10 minutes. And I said, well, you know, we could go on for another 5 minutes. And Dave said, well, I haven't prepared it yet.
I was Dave's TA for the intro cognitive psychology class, and I would go to lectures and everything he said just seemed so deep and profound. And the students would say to me, what is this guy talking about? You know, he isn't very engaging. He isn't selling this work to me. And I just had such a different perspective than the students did.
Do you think now, like everyone else feels, so I guess like role model, you try to be like them, or do you kind of see yourself like that?
I would be thrilled if I had some tiny fraction of the ideas Dave has, but yeah, I don't care very much about publishing and promoting work. I don't have a Twitter account.
Oh, you should get up to date with the times, Mike.
So online.
Hashtag 70 years. That should help.
I guess I'm really curious about the kind of interdisciplinary nature of your experience. And I was just wondering, like, how important is that for you for idea generation? And I guess a related question, like, how important do you think that is for progress, for making progress in like AI research in general?
I feel like at Google, I've been trying to figure out where I fit in and what I can contribute. And I'm pretty convinced that the only thing I have to offer is that interdisciplinary perspective. And I think one of the payoffs of having been around for a while and having experience in lots of areas of cognitive science as well as machine learning is that I can draw those connections. So pretty much every paper I write, even if it's a machine learning paper, has a cog-sci pitch to it. And it really helps to ground the work for me in that interdisciplinary pitch. And it's what, to my mind, I'm doing differently than all these other people who can do, you know, big implementations far more effectively than I ever could, and who are up on the latest, greatest little tricks that folks use that are part of the deep learning religion. But yeah, no, sort of being able to draw in cog-sci and its relevance. I'm just starting a line of work with a whole bunch of people now that's focused on what can we learn about early representations in the visual system, and can we incorporate them into models as part of the input as a form of inductive bias separate from like convolutional architectures to get networks to learn the right kind of things. So just as a for instance for that, it turns out there's this beautiful psych literature on how people can very quickly in parallel across the visual field extract 3D structure. And our models treat 3D structure extraction as sort of a final stage of processing in vision systems, like if you're doing segmentation or whatever, but not as part of the input. And all the evidence psychologically is that the depth cues are really there from the earliest stages of processing. Now, where they come from, I'm not sure, but you can ask, what happens if we augment input representations and don't just go RGB, but have RGB inferred X, Y, and Z? What can we learn and what sort of robustness will we get? And that's definitely cognitive science inspired. There's a whole bunch of features that psychologists have studied, things like symmetry and convexity that the brain seems to extract very quickly. And the brain suppresses homogeneous regions in the input, even if they're complicated textures. And if we could do that kind of suppression, would it help focus attention? There's a lot of vision that's task-based rather than willy-nilly bottom-up. Most of the time when we're using our eyes, we have some goal in mind. And so if we have a more task-driven visual perception, what sort of effect that will have. So I feel like there are all sorts of opportunities to leverage the CogSci data in consideration of AI.
Actually, things are changing a lot right now. So the graphics people have come up with neural radiance fields, and you've probably seen these demos now where you can take a scene and show it from different angles very effectively. And that's taking 3D seriously at low levels.
Oh, I should know more about that. Thank you.
Yeah, it's going to revolutionize things.
Cool.
So I want to end on one last question, and this can be for both Mike and Jeff. I want to give you both an opportunity to highlight a paper that it's either yours or not yours that you think is underrated. We've talked a lot about historical papers and bringing it back to today. So what is a paper that you think is underrated that we should all go read?
I'll let Jeff answer for himself, although I think every paper Jeff's ever written is underrated in the sense that it deserves even more attention than it receives. In my case, I had a whole line of work in the early 90s on sort of hybrid symbolic subsymbols and the interface between neural representations and more symbolic representations, and building models that sort of had inductive biases to make representations more symbolic and to go back and forth between symbolic and subsymbolic representations. Included in that work, I have to get a little snide remark in here, was a model that learned to push down automata, and it was all continuous and differentiable. So that stupid neural Turing machine wasn't the first fully differentiable external memory model. Pisses me off, but my student Sri Rupa Das did this in the early 90s, and she spent 6 months computing derivatives by hand to backpropagate through a stack, a continuous stack. So, but in any case, that interface, sorry, I didn't mean to digress, the interface between symbolic and subsymbolic representations, which it's having a heyday now as well in the field, because there's so many people working on so many things.
I can answer for me, which is there's a paper in NIPS in about 2005 called Inferring Motor Programs from Handwritten Images of Digits. And that's basically about the analysis by synthesis view of perception. And particularly about the idea that the natural domain for understanding images of digits is the motor domain. That was a paper that was rejected by NIPS, by the referees, basically. They gave it bad reviews. And then Yoram Singer was on the program committee. At least, I have this from Yoram Singer, and I assume it's right. Yoram was on the program committee and said, this is a really interesting paper, and I don't care what the referee said, it ought to be published. And so it's squeaked in because of Yoram, and has since been widely ignored.
I thought you were going to tell a different story about a paper that was rejected that you then used for an invited talk at the same conference.
Oh, yes, yes. That's got more publications now. It was the first paper on capsules. I couldn't get anybody to publish anything about capsules. I submitted papers to conferences, and my friends on the program committee, like Kevin Murphy and somebody else, I can't remember the other former friend on the program committee, they said, well, you know, I said, why did you reject it? And they said, well, it's not ready for publication yet. And I eventually got invited to give a talk in Finland at a conference. Now, I can't sit down because of a back problem. So it took me 11 days to get to Finland without sitting down, and then 11 days to get back again. But I spent 22 days getting to Finland so I could give this talk. And after I'd agreed to give the invited talk, I said, can I submit a paper to go with the talk? Because I figured this was the way to get it published. And so they said, sure, but we'll have to get it refereed, but of course it'll be accepted. And so they got it refereed, and the referees rejected it. But they knew me, and they knew I'd talk about it anyway at the conference, and I'd say it'd been rejected by the referees. So they went and found a referee who was a friend of mine who told them they could accept it. That was the first paper on, that was called Transforming Autoencoders. That was the first capsule paper. And the point about that was it was a neat idea. There was nothing that worked very well. Well, there was one thing that worked quite impressively well because Alex Krzyzewski was involved, but apart from that, it didn't work very well. But I wanted to get the idea out there, and it's very hard now to get novel ideas out there. Because what happens is the referees are graduate students or postdocs, and they're scared of accepting something they don't understand. And if they read something they don't understand, they think, oh my God, this makes my brain hurt. And they write a review saying it wasn't very well explained. Well, if they read a paper that says, we tried this on the 15 standard databases and 6 more, and on sort of 17 of these 21 databases, it did slightly better than the state of the art, then that's an easy accept, right? Even though the idea may be just completely trivial. You know, the idea might be something like, well, actually, as the learning progressed, we increased the mini batch size. Well, that's sort of interesting, but it's not a big idea, right?
So Jeff, we'd love to do a retrospective with you as well. We can give you the spotlight that next time. Maybe Mike will help interview. That would be a fun conversation. We can follow up about that after this.
I think we should delay it a bit because I haven't done my best work yet. Thank you. Mike is always very, very flattering. I don't quite know why, but
Well,
I have to tell a story about Mike. I once met him in queuing for a plane at Heathrow, and it was the early days of laptops, and I had my laptop with me, and it was a long queue. So during the long queue, I gave Mike several lectures using my PowerPoint on my laptop. Do you remember that?
I absolutely remember that, and I was one of those people whose head was swimming with the idea and couldn't quite digest it, and feeling frustrated that so much was being thrown at me all at once. And I knew it was really good ideas, but as usual, when we talk about new ideas, it takes me 6 months to catch up with what you've said in the first 20 minutes of a talk. So
You see what I mean about flattering?
just truth. Thanks for joining us, Jeff, and thank you all for listening to us blabber.
Sorry I wasn't here at the beginning.
We all learn from one another.
Research retrospectives are a series of conversations
that dive into a researcher's technical body of work
to understand how papers build on top of each other
and create a legacy.
We learn about paths not taken,
serendipitous events, collaborations,
and setbacks that shaped their research.
Our interviews are informal, friendly, and fun.
and welcome to Retrospectives.